how this single contiguous memory management system work. How this particular single contiguous memory management works. So we are working with first method called single contiguous memory management. Okay, so as I said that this particular memory management we will study in terms of 4 segments, that is concept, then hardware, then how the software is going to be, and how the advantages and disadvantages of systems are. Okay, so or the method is, so the concept we are going to study. Okay, so let us work out on this concept part. So this particular memory management is the simplest memory management method. This particular memory management method is adopted by SUST OS, okay, or we can say uh, single user, single tasking operating system, right? So this particular method is being used by single user and single tasking operating system, where there is no concept of multiprogramming. There is no concept of multiprogramming. In simple case, so there is no multiprogramming involved. So which means that no multiprogramming concept of multiprogramming, which means here we are going to just I'll just write it as no multiprogramming. So this will give you more idea. So this is no multiprogramming which means one-to-one correspondence between one-to-one correspondence between user task or process, or you can take as job, right? One-to-one between like user relationship between user, task, process, job, or and the resources. So this is important. User, task, process, job, and resources. There is one-to-one correspondence. So which means if you look at the representation of memory, so we know that like the memory, say this kind of organization we are going to have. So we understand that with this particular memory, we have certain size of this particular memory, say from this to this. Let us try to understand that this particular segment of memory is say 1000K. For just simple calculation, this is say 1000K. So here 1000K is the total memory, size, right? So 1000K is the total memory size, and we understand that with this particular 1000K, some portion of this particular memory is allocated for whom? Allocated for OS. Say this is 100. So the 100K memory is being allocated for the operating system. So this is OS. This is OS. And this particular segment, which is left over here after allocation of the operating system, right, is this is allocated for user job or task or a process. Okay, so this is allocated for user, job, task, and process. So which means that out of this particular 1000K, 100K is allocated for the operating system. So which means that this particular 900K, is allocated for user space. Okay, so which means that if you have a task, say if you have a task T1, this task T1, if it is say, if this task is say task T1 is say 901K, right? So task is 901K. T1 task is of 901K. So simple case is that you need to see whether it is fit into this. So again here the policy we need to see. First policy, keep the track and what? Status of memory. So here this memory, this particular here, this memory means not whole memory. It is user space particularly. The space which is reserved for user task is user space. So we can say here we will keep the track and the status of user space. Okay, okay, track and the status of user space. Okay, now when it is a status, there are only two status here. One is allocated and second is free. Okay, so at this particular point of time, we don't have any processes allocated into memory. So means what? The status of this particular 900K is free. So we'll just write here status as free. So the status is free now. Okay, then we need to just think of the second point, like if it is free, then how do we allocate it, right? So if it is the status is free, then you need to decide a policy to allocate. So second important point is we need to design the policy to allocate task oblique job oblique process into user space. Okay, so which means when we say that design the policy, which means we are trying to think of a process or a method. We call it as a software kind of thing. Okay, so which we will say the software we need to see. Okay, so this is going to be done. So means if we design the process, then we can specifically, third point is allocate the user space available to the process, to the task, job, or process of user. Of whom? Of user. Okay, and then fourth important point is if it is being allocated, then you need to deallocate once the task oblique job oblique process is over. Okay, so this is the policy. So conceptually, you need to see the memory management, which is simple here. This is adopted by single user single tasking operating system, where no concept of multiprogramming is involved. No concept of multiprogramming means one-to-one correspondence between user, task, process, and job, and the resource. So for example, in this case, example is this: the memory is being divided in two sections here. One section is reserved for operating system, and second section is reserved for user task. Okay, so this is logical separation. Please try to understand, this is logical separation. Physically, you cannot divide a memory. So this particular separation is a logical separation. So you need to understand this particular important policy. These are the 4 points that you need to understand. Okay. So whenever you are doing this, there is logical separation. This is important. Logical separation. Logical separation in between what? Logical separation exists on what? On primary memory. On primary memory. Conceptually, there is a logical separation. Okay, now to perform this logical separation, what we need to do is that we need a hardware. So we don't need any special hardware as far as this policy is concerned, as far as this single contiguous memory management is concerned. No special hardware is required. Hardware is required for us. Okay, no special hardware is required. Only the hardware which we require is called as bound register. So bound register decide boundaries. Okay, decide boundaries. Boundaries of what? Like say there is one section of OS and one section is user space. So just to decide the boundary in between OS and user space, what we need? Bound register. These bound registers are particularly providing what? These bound registers are particularly providing a hardware protection, hardware protection means what? Whatever the users is going to allocate a particular task into this particular user space, that should not access any information from the user operating system's allocated space. To protect this OS, that this should not be accessed by the user space, as well as OS should not access the user allocated space. So in this case, just to those two sections separate, we have a bound register required. So the logical separation bound register is used for this. Okay, and this bound register will hold address of the protected area and the protected area. So protected area. So here in this case, it has two protected areas. One is area reserved for OS, right, and area reserved for user space. Okay, so this two information exist into these bound registers. Okay, so as far as this case is concerned, we have to look at conceptual part. So this is at the conceptual part. Okay, now but if you look at this status of this particular memory user space, which is free right now, then we need to decide a policy to this. Okay, so in case of this policy, one thing is decided that you are allowing only one task uh, of user at an instance of time. So which means you need to decide a strategy, like okay, you are going to say, as far as hardware is concerned, as far as software is concerned, what we are going to do is like say uh, say start, we'll say start, and then uh, at first what we are going to check is task size is less than or equals to available memory. Available memory. So there are two conditions. Either it is say yes, or it is say no. What if it is no? What if it is yes? If it is no, so simple case, you have to just announce that you have insufficient memory. You have insufficient memory. Okay, because the task size is greater than size available. If yes, then simple, what you need to do, allocate memory to the task. Next, update the status of memory. Okay, uh, update the status of memory, and next is release memory upon use. This is the agreement, right? So release the memory upon use. So in this case, just take a case. We have a task T1 which is of 901K size and available spare memory is 900. So our software says that is the task size is available. Task size is less than or equals to available memory. So 901 and 900. So no, you cannot accommodate, because if you want to accommodate T1, the size of T1 should be less than 900K. If it is less than 900K, then only we can go for allocation. So here, what in this case, in case of T1, we will simply announce that you have an insufficient memory to accommodate T1. Okay. Now, if you have T2, just let us case if you have next task T2, and which is of 600K. Just look at how our algorithm works. You have a task start, then each task size is less than or equals to available memory. Task size is 600. It is less than the available memory. Available memory is 900. Okay, so and status is free. If it is 900 and this is free, then allocate the memory to the task. So simple case is that we will say that this particular portion is allocated to 600K. So we have now we have three portions here now. Three portions here. One is T2. Then we have this segment as 300K free. Let's say 300K free, and the status, instead of status free, it is we are going to allocate it. Okay, and we allow only one task to remain present. So what if we say, for example, we have one more T3 and it is of 100K. It is in queue, for example. So can we allocate T3? No, we cannot allocate T3 because we have in memory as a 100K, as a 300K, but we cannot allocate T3 here because we understand that there is one-to-one relationship between task, process, job, and the resource. So only one task remains active. So once this is going to be deallocated from memory, then we are going to go for T3. So for T3 means once T job, then we can go for T3. So if you look at this particular mechanism, there are certain advantages. What are those advantages? This method is very simple, right? Easy to understand and implement. This is very easy to understand and implement. Okay, but at the same, this has certain disadvantages. Disadvantages. First, and the very important disadvantage is Can anybody tell me here? The first, the most important disadvantage is poor utilization of memory. We have very poor utilization of memory. At the same, we have poor utilization of processor also, right? Poor utilization of the processor also here. We have poor utilization of the processor also. And third important is being a limited size of the job. Of being a limited size of a job. Just a minute. Being a limited size of a job. Being a limited size of job. It must be fitted as per what? Available space. It must be fitted as per the available space. So this is important. Okay. So as far as single contiguous memory management is concerned, we have this particular thing. So as a conceptual part, what you need to understand is this. As a conceptual part, we have to understand this that this is a simple method, the simplest method for memory management, because you can see it is very simple. Advantage is very simple and easy to understand as well as easy to implement, right? So this is adopted by the most important point. This is adopted by single user, single tasking system. Right, so this is adopted by single user, single tasking system. This is important, and there is no multi-programming as such involved here. With that, user, task, and process and the resources, there is one-to-one correspondence. Okay, so one-to-one correspondence is existing. So as far as policy is concerned, it keeps the track and the status of the memory. Design the policy, allocate the job, task, job, process into a user space. Okay, then you need to allocate that as per the policy. Then you need to allocate the job. So as status is concerned, we have only two status available here. If I allocate F for free, that's it. Okay, so task is a task whether the memory is allocated or free. So it has to be considered in the software part. So in case of software, which we are going to do is we are going to check whether the task size is available into memory. Okay, if the task later we can simply modify it, like if the task size is available into memory, and here we can also check and status is equal to free. Okay, we'll just modify it, right? Is the task size is less than the available memory, and if the status is free, yes, then allocate the task, update the status of memory. Now here the update is means from free to allocated. This is, we are changing the status here, free to allocated. Okay, so if it is done, then you need to release the memory upon the use, right? If not, if this is simply, you can announce that you cannot accommodate the task into the primary memory. Okay, as far as logical, as far as hardware is concerned, we need to see that bound registers are used. No special hardware are required. They're inherent actually. Their thing is inherent. So no special hardware is required, but whatever the hardware that we are in need of is called as bound registers. We are called as bound registers. Okay, so these bound registers are used. So where the logical separation exists, so on primary memory, then the hardware which we are using is called bound register. It decides the boundaries. Uh, these boundaries are in between the operating space allocated for operating system as well as the space reserved for user space, user address. So hardware, this bound register is specifically for hardware protection, and it holds the hardware. It holds the address of the protected area, right? So protected area of operating system as well as user space. So I